Good morning, chemistry students. Here are your Chapter 8, Day 3 notes. We're going to be starting in Section 8.2 and going through and finishing up the information about single replacement reactions. So we're going to start to learn, or you're going to start to learn about the types of chemical reactions and how to classify a reaction as one of the types. So Section 8.2 is titled Types of Chemical Reactions, and we're going to start by talking about classifying the reactions. And there are 5 general types. And if you scan your outline, you'll see them. One of the types is a combination or synthesis reaction. The ChemQuest we did called it a synthesis reaction. Your textbook calls it a combination reaction. The second type we're going to talk about is a decomposition reaction. Third type, and the one we're going to finish up with today, is the single replacement reaction. The next time after this that we do notes, we'll talk about a double replacement reaction. And last but not least, we'll talk about combustion reactions. And do keep in mind that these reactions may be classified as more than one type. These are pretty standard types of reactions that most of you probably will also encounter when you get to college, if you have to take a college chemistry class. But do know that sometimes you encounter a reaction that actually could fit into more than one of these categories. For the most part, the ones that you're going to do, typically it's going to be pretty clear which one of these 5 types of general reactions the reaction should be classified as. And again, just looking at the names themselves can start to give you a little bit of an idea about what to expect, right? Combination synthesis. So we're going to make something in a combination or synthesis reaction. Decomposition, right? Something's going to break down. Single replacement, you've seen on your ChemQuest a little bit already, right? Single replacement, one atom is somehow going to get replaced. Double replacement, 2 atoms are going to get replaced. There's going to be kind of a swapping. And combustion, right, to combust means to burn. We're going to be talking about burning something. So we're going to start by talking about combination reactions. Again, your textbook calls it combination. The ChemQuest we did called it synthesis. I don't really care too much which one you call it, okay? They're the same thing. The definition of a combination or synthesis reaction: 2 or more substances combine to form a single substance. So again, it's kind of what we already said, right? We said we were going to probably be making something. Notice here we have 2 or more substances that are going to combine to form just one substance. If you think about that a little bit, one of the things we're going to talk about with all these reactions is how many reactants and how many products there are. So if you think about this definition we just said, right? For this reactant, there's always more than one. For you, they're usually going to be 2 elements. Okay, but it could be 1 element and 1 compound, or it could be 2 compounds. Most of the ones that you're going to do are going to be 2 elements. Okay, but you could take an element and a compound and create just 1 compound as a product. And you even can take 2 different compounds and create just 1 compound as a product. Again, if we look back at our definition of combination or synthesis reaction, we see again 2 or more substances combine to form a single substance. So for products here, okay, there's usually only one. For your purposes, there will just be one. And it's always a compound. Combination reactions, it's really hard to predict what the product will be. So typically what that means is that most times you will not be asked, you won't be given the reactants and asked to say what the product is going to be. You will be asked to do that for many of the other types of reactions, but not typically for combination or synthesis reactions. So our example, okay, our sentence is the formation of aluminum chloride from its elements. Okay, so our sentence for this is the formation of aluminum chloride from its elements. Now again, this is a sentence, and remember kind of our steps that we follow to write and balance a chemical equation, which is what we're going to try to do here. Okay, this is our sentence. The first thing we want to do is our word equation. So again, I'm going to try to put that actually a little bit more in the middle. There we go. So again, we want to put our arrow in the middle, and then we want to read our sentence and decide where things go. So notice it's the formation of aluminum chloride. The formation tells us that this is actually the product. And it doesn't specifically give us what the reactants are, but it tells us it's from its elements. So the only elements here are aluminum and chlorine. And it's chlorine, not chloride, because again, it's not in a compound. So that's our word equation. Again, we've written our word equation because it helps us focus on what's important. So now we're ready to write our skeleton equation, right? So we're going to take all of our words and make them symbols. So our symbol for aluminum is Al. Chlorine is Cl, and I usually make it kind of cursive-y. Now, chlorine, remember, should be Cl2 actually, because chlorine is part of Mr. Brinkelhoff, which means that when chlorine is not in a compound, when it's all by itself as an element, it always exists as diatomic chlorine. So it has to be Cl2. Now, aluminum chloride, that's a compound. So again, we have to ask, is this ionic or molecular? It's an ionic compound because it's a metal. So again, we're going to write our symbols, write our charges, crisscross, make sure it's the lowest whole number ratio. Our symbol for aluminum is Al. Our symbol for chlorine is, and its charge is +3. It's in group 3A, so it loses its 3 valence electrons. Chlorine is Cl, and it's in group 7A, so it has a charge of -1. We crisscross down and we get AlCl3. So now we're ready to balance this. So I have one, and I'm going to kind of grab a different color here. Let's do this. So I have one aluminum here, and I have one aluminum over here. I have 2 chlorines here, and I have 3, so I have to make them equal. So I'm going to put a coefficient of 2 in front of aluminum chloride and a coefficient of 3 in front of chlorine. So now I have 6 chlorines and 6 chlorines, but now I have 2 aluminums. So I need a coefficient of 2 in front of aluminum. I think it's balanced. I'm going to double check. 2 aluminums on the left, 2 aluminums on the right. 3 times 2, 6 chlorines on the left. 2 times 3, 6 chlorines on the right. So this is correctly balanced. So combination reactions, I always have more than one reactant and I have a single product. Okay. Again, that's going to be important because at some point here shortly, you're going to be given a whole list of reactions and you'll only see the reactants. and you'll be asked to predict the products. And one of the steps to predict the products is that you have to be able to identify what kind of reaction it is. If it's a combination reaction, you're probably, and if it's asking you to predict the products, it's probably going to be two elements as your reactants. All right, our next kind of reaction we're going to talk about is our decomposition reactions. The definition of a decomposition reaction: a single compound is broken down into two or more products. A single compound is broken down into two or more products. Again, as we look at this definition, it tells us something about the number of reactants, right? We see it's a single compound. So in terms of our reactants, it's always only one. Okay? And it's always a compound. And then again, our definition really gives us a clue about the products as well, because it says there are two or more products. So our product, we're just going to say that there's more than one. It may be two elements. It may be two compounds. Or it could be one element and one compound. And because of all of that variety, again, generally for you, it's hard to predict the products. If you're asked to predict the products, likelihood is it's going to say that it's some sort of compound that decomposes into its elements. For a decomposition reaction to take place, they usually require some form of energy to take place. Like heat, light, or electricity. A kind of good example of a way to think about that a little bit is in the winter, right? When a deer gets hit by a car and it's on the side of the road and it's cold outside, it freezes and it really doesn't start to decompose. But in the springtime, when that frozen deer has now melted, and then it's a nice, hot spring day with lots of sunlight, you can tell where those dead deer are if you drive with your windows open, because you can smell them, because all of a sudden they really start to decompose. So that deer doesn't do much decomposing in the winter because we don't tend to have a lot of light and there's not heat. Okay, but as soon as it gets nice and warm outside and it's a nice bright sunshiny day, you can smell that decomposition taking place. So decomposition reactions need some form of energy in order for them to take place, such as heat, light, or electricity. Our example of our decomposition reaction is going to be that calcium carbonate is heated to produce calcium oxide and carbon dioxide. So again, this is our sentence. The first thing that we're going to do to work towards getting our balanced chemical equation is we're going to make this a word equation. Calcium carbonate is heated. So that means calcium carbonate is our reactant. Now again, we can indicate that heat by putting that little triangle symbol over our arrow. To produce, so calcium oxide is a product. We have an and, so a plus, carbon dioxide. So now that we have our word equation, now we're going to go ahead and do our skeleton equation. So calcium carbonate, that is an ionic compound because carbonate is one of your polyatomic ions you have memorized. So again, we're going to write our symbols, we're going to write our charges, we're going to crisscross, and we're going to make sure it's the lowest whole number ratio. Our symbol for calcium is Ca. It has a charge of +2 because it's in group 2A. Carbonate is CO3, charge of -2. Again, I could crisscross down these 2's, but then I'd have to reduce them. So I'm just not going to do that. Okay? And we're heating this, so we can put our triangle up there again. And then calcium oxide. Again, that's an ionic compound because calcium's a metal. So we're going to write the symbols, write the charges, crisscross, and make sure it's the lowest whole number ratio. Our symbol for calcium, again, is still Ca with a charge of +2 because it's in group 2A. Oxide is O with a charge of -2 because it's in group 6A. Same thing, right? I could crisscross down, but then I'd have a 2 and a 2, which I'd have to reduce to a 1 to 1. Plus, carbon dioxide, that's a molecular compound because it's 2 nonmetals, and our prefixes become our subscripts. Well, we don't have a prefix, it means 1, so that's 1 carbon and 2 oxygens, which you probably knew. Now, looking to balance this, I have 1 calcium, I have 1 calcium. And I can't count carbonate as a group, so I have to count it separately. So I have 1 carbon, 3 oxygens, 2 plus 1 more makes 3 oxygens. So this happens to be a skeleton equation that is also a balanced chemical equation. So again, so far we've talked about 2 types of reactions. To identify a reaction as a combination or synthesis reaction, I'm going to look for 2 reactants and only 1 product. To identify something as a decomposition reaction, I'm going to look for a single reactant and multiple products. Single replacement reactions are the last type of reaction we're going to talk about today. Single replacement reactions are also sometimes called single displacement reactions. So again, I'm just giving you both names. I don't want you to get to college chemistry and go, I've never heard of a single displacement reaction. It's exactly the same thing as a single replacement. Okay? It's just 2 different names for the same thing. The definition of a single replacement or single displacement reaction is that atoms of one element replace the atoms of a second element in a compound. Again, we've seen these on your ChemQuests, and basically, again, what was happening here is the element that is all by itself. If it's a metal, it's going to take the place of the metal in the compound. If the element that is all by itself is a nonmetal, it's going to take the place of the nonmetal in the compound. Okay, so the element is taking the place of the atom that it's like in the compound. Again, as you kind of think about this then, in terms of reactants, there are always 2, and they are always 1 element and 1 compound. So I have to have an element that's taking the place of whatever is like it in the compound. In terms of products, there's also always 2. And again, it's going to be 1 element and one compound. It won't be the same element and compound, because if it was, then the reaction wouldn't take place. You wouldn't have any new substances formed, okay? But it'll be a different element and compound. For these, you must be able to predict the product. You're going to have lots of these reactions where you're just given the reactants and asked to figure out what the product is going to be. So our dating example here, we're going to kind of talk about superheroes, I guess. So we have Wonder Woman and Superman and Batman, because those are the first three that come to mind. So we have, and I think Superman's stronger than Batman. So I'm going to say that Batman and Wonder Woman are out on a date. And Superman is lonely. And he kind of is checking out Wonder Woman and decides that Wonder Woman is the woman of his dreams. So I guess he's leaving Lois Lane. Okay, Wonder Woman is the woman of his dreams, and so he wants to sit down and have dinner with her and get Batman out of the picture. So he decides that he's definitely bigger and stronger than Batman, so he walks over there and he kind of pushes Batman out of the way, and he sits down at the table and has dinner with Wonder Woman. Okay, that's what's happening in our chemical reaction. The element that is by itself wants to be bonded and in that compound. So, because it's going to be stronger than the element that's like it in the compound, it's going to push that element out of the way and take its place. Okay, so that's kind of our dating example. So the element in the reactant must be stronger than the element in the compound for the reaction to take place, right? So I said that Superman was stronger than Batman. Batman was already in a relationship, right? He was already bonded to Wonder Woman. For this reaction to take place, Superman has to be stronger than Batman. He has to be able to push Batman out of that reaction and take his place. So the element in the reactant that's all by itself must be stronger than the same type of element in the compound for this reaction to take place. So since I feel that Superman is stronger than Batman, if it was Superman and Wonder Woman were already out on a date and Batman came in and he kind of wanted to sit down and have dinner with Wonder Woman, because I feel that Batman's not as strong, that wouldn't be able to take place, because Batman's not strong enough to push Superman out of the way. Okay, so the element in the reactant must be stronger than the element in the compound for the reaction to take place. Now, how are you going to know that, right? Because I'm talking superheroes and opinions, right? So we have to have a way to know this. So the element that is by itself, okay, must be higher on the activity series than the element in the compound. So the one all by itself has to be stronger than the one that's like it in the compound. Again, how are you going to know? You're going to use the activity series of metals, okay, which is page 217, table 8.2 in your textbook. The activity series of metals lists the metals in order of decreasing reactivity. What that means is my strong metals are at the top of this series and my weak ones are at the bottom, which means the element that is alone or by itself must be higher to do the replacing. So you have a chart in your outline to fill in. So if you want to open up your textbook to page 217 and look at this and copy it down into your outline, and you can pause the video if you need to. Right, so again, what I've said is the strong elements are at the top, the weak elements are at the bottom. So if I'm going to compare lithium and aluminum, lithium can replace aluminum from a compound. But aluminum cannot take lithium's place because it's not strong enough. Okay, so stronger at the top, weaker at the bottom, and we have this little caveat at the bottom that the metals from lithium to sodium will replace hydrogen from acids and water, and from magnesium to lead they will replace hydrogen from acid only. Okay, so this is our activity series of metals. And what this means is that sometimes you won't write that there are products because sometimes the reaction won't take place. Again, in my example, if lithium is reacting with aluminum in some compound, that reaction will take place because lithium is higher than aluminum. If it was the other way around and aluminum is reacting with lithium in some sort of compound, I would write no reaction as my products for this one because aluminum cannot replace lithium from a compound. So if the reaction won't take place, don't leave it blank. Okay, write no reaction for the products. So you still need to have your reactants written in chemical symbols, but instead of writing the products like the formulas for them, you would write no reaction because the reaction doesn't take place. So there aren't really any products. Now, this is when you have your element is a metal. Sometimes your element is a nonmetal, in which case we're talking typically about the halogen reactivity. Remember, the halogens are group 17 or 7A. Okay, so those are the halogens. And their reactivity decreases as you go down the group. So again, we're talking about these guys, these guys over here. And again, what I'm saying here is here's where we're strong, here's where we're weak. Okay. So if it's non-metal, it's going to be a halogen as your element. So let's take a look at an example. We're actually going to look at two examples. So in the space you have to have room to get two examples in there. So our first sentence is going to be that magnesium reacts with silver nitrate. And notice that I'm not giving you your products. I'm doing that on purpose because you need to be able to predict the products of this. So here's our sentence, and we want to first write our word equation. And again, we know that these are both our reactants. So we have magnesium plus silver nitrate. Now again, when we think back to our definition of this, okay, we said that the atoms of one element replace the atoms of a second element in a compound, and it has to be the same kind. So we want to kind of look at magnesium here and say, what kind of element is magnesium? Well, it's a metal. So it's going to take the place of the metal in the compound silver nitrate. Which one of those is the metal? Silver. So these are the two that are swapping. Now, I should check my activity series real quick. I need to see that magnesium is higher than silver. So here's silver, way down here at the bottom, and here's magnesium. So magnesium is above silver, so this reaction is going to take place. So silver is going to be all by itself, and magnesium is going to be bonded to nitrate. So they just swapped. So now that I have my word equation, I'm going to write my balanced chemical equation. My symbol for magnesium is Mg. Silver nitrate, nitrate is a polyatomic ion, so we know it's ionic compound. So we're going to write our symbols, we're going to write our charges, we're going to crisscross, we're going to make sure it's the lowest whole number ratio. Now silver is in the short columns of our periodic table. So we do want to check our helper sheet. But notice that silver only has one possible charge here. Okay, silver only has one possible charge. So I know that silver is going to have a charge of +1. So silver is Ag with a charge of +1. Nitrate you have memorized is NO3 with a charge of -1. So I'd crisscross down ones, so I don't need to do that. Now silver is my product. So silver by itself, and magnesium is Mg. It's in group 2A, so it has a charge of +2. Nitrate is still NO3 with the charge of -1. I crisscross down and I'm going to need parentheses and a 2. So now I'm ready to go ahead and talk about balancing this. I have one magnesium and I have one magnesium. I have one silver and I have one silver. I have one nitrate and I have two nitrates. That means I need a coefficient of 2 in front of silver nitrate. Because I now have two silvers, I need a coefficient of 2 in front of silver. Checking, right? Kind of doing my check step. One magnesium, two silvers, two nitrates. This is properly balanced. Our second example, magnesium reacts with lithium nitrate. Once again, notice I haven't given you your products, I've just given you your reactants. So again, our first thing to do is we're going to write our word equation. So we know magnesium is one reactant. Our other reactant is lithium nitrate. Again, I want to check my activity series. Magnesium is a metal, so it's going to take lithium's spot. So magnesium needs to be up above lithium. Notice that it's not. So what I'm going to do for this one, okay, is I'm going to write no reaction. Now, I still want you on a test or quiz to write the chemical formulas for magnesium nitrate. So this really is a word equation. It's not a balanced chemical equation. So I still want you to write magnesium, which is Mg. Lithium nitrate is an ionic compound, so Li, it's in group 1A, so charge of +1. Nitrates, NO3, charge of -1, so nothing to do to that. And then write no reaction. So I still want you to have the reactants written out in chemical formulas. Okay, but you won't write any products because the reaction doesn't take place because lithium is not strong enough to, or sorry, magnesium is not strong enough to push lithium out of this nitrate. Okay, so this is no reaction because, and again, magnesium is below lithium on the activity series. So we write no reaction. So that is the end of our notes for today. You don't have any homework, so enjoy your afternoon and evening. I'll talk to you tomorrow.